Hello AP Electricity and Magnetism students. We're here in my basement where I've been running my dehumidifier all weekend long, full blast, to try and get the air as dry as possible so we can do an experiment with electrostatics, the balloon charge experiment. So the reason why we need the air dry is because if the air is humid, then the charge that you put on any object tends to leak off into the air. And so you don't get any results. Sometimes in years past when we do this experiment in a classroom, there's no dehumidifier in the classroom, so it often doesn't work. But here in the basement, hopefully the air is nice and dry and we'll get some good results. So balloon charge experiment, of course, you don't have to print this out, the instruction sheet. But at this point, hopefully you have printed out the instructions. So here is the first page of instructions. And then the second page is really where we're going to fill in our data here. So that's what we're going to do now. I'm going to collect data, but I just want to tell you that don't write the data that I'm writing down, that I'm measuring, because everyone will get their own data. I'm going to put a spreadsheet into Google Stream, the Google Classroom, and in that spreadsheet you'll get your own data to analyze. The reason why we're here together now is so you can see where that data came from. Okay, so basically what's going to happen is we're going to hang two balloons on strings, pieces of thread, as you see in the picture here, and then we're going to charge those balloons up, and because they're both going to be negatively charged, they're going to repel like this. They're pushed apart, and so gravity would cause them to fall down and hang straight down and touch, not quite straight down, but touch. But we're going to get them to repel, and then hopefully what we're going to do in the end is we're going to figure out the charge on the balloons from how far apart they're swung outward. And then also, after a couple minutes, we'll measure again, and then we'll see that the balloons have decreased their angles slightly, and that means they lost a little bit of charge, and we'll be able to calculate the rate at which they lost their charge, okay? The rate at which the charge leaked off into the air. So that's basically the experiment. I'm not going to read through it because you'll just watch me do the procedure. So what I've already done is I've blown up the balloons, attached them to strings, okay, and then fed those strings through a protractor. So when you may not be able to see these strings, but when this balloon goes out to the side, maybe I'll do it by my white shirt, you'll be able to see it. When the balloon goes out to the side, you'll be able to see, we'll be able to see the angle at which those balloons swing outward, and from that allows us to get the calculations. So the first thing is we need some preliminary data on the balloons. So what I have here is an electronic balance, and I'm going to measure the balloons on my little table here, which you can't see, but I'll just show you my electronic balance here. Okay, so and then let me zero. Okay, it's zeroed, and I'm going to just set this down. Okay. See if it stays. Okay, so I get a mass about 3.2 grams of, again, you're not going to jot that down because you will have your own data, but I will write down 3.2 grams, and I'll mass the other one, and they should be the same, but I didn't blow them up exactly the same, plus they're made in manufactured, maybe the rubber's not equal thickness, so one might be a little bit more. Yeah, this is showing 3.3, but we'll average those because otherwise the analysis gets too complicated if the balloons are not of equal mass. Okay, so the other thing that I have to measure on the data sheet, if you look below M, there's a symbol capital D, and capital D is the diameter of the balloon. So I will measure that with a meter stick, okay, which I have right here. Oops. And this is going to be a little hard to estimate, but looks like I'm going to say this one's 27 centimeters. And I'll measure the other one also. And again, we could take an average. This one's showing 28 centimeters, slightly larger. Okay. Again, you're not writing those down. I'll give you your own measurements to analyze. Okay, the other thing that we need are the lengths of the strings to the protractor. So I will put this up at the balloon and I'll measure this way and I get 74 centimeters. And once again, I'll do that with the other string. Oh, there we go. Wow, must have gotten tangled. That can't be right. Hold on just one second. Maybe you have to let one string out a little bit more. Okay. Let's try it again. Okay. That one's still 74 centimeters and this one's now 72 centimeters. I guess that's close enough. I don't want to hold you here too long while I am fiddling with the measurements because once again, this is just to show you what's going on here and then you'll get your own data later. Twist it up here. All right, so now what I'm going to do is tape this onto this rafter. Let's see, let's go more in the middle here. And hopefully you could see that protractor. Okay. All right, now move this to the side. What I'm going to do is charge these up now. The way I can charge them up is just by rubbing them with some fur. And the fur will deposit some electrons onto the rubber of the balloon. Okay, there we go. All right. So they like to attract to me now, so I'm going to try and stay away and let this get to equilibrium. Now, to read that protractor gets a little bit difficult because the balloons will just keep pulling toward me. So what I'm going to do is I'm going to take a photograph of the strings so that I could just read them later. So let's see, zoom in. All right. Okay. Okay, so, and I'm going to start my timer now. So in 2 minutes, we'll make the measurement again as those lose a little bit of charge. Now, I'll hold this up to the camera, and I don't know if you'll be able to read it that well, but see, you can see that there are some measurements that we could make on either side. From the 90 out, I see on one side, we go out, swing out about 11.5 degrees, and on the other side, maybe like 11.8 degrees, so not quite symmetric. I'm going to write those both down. Actually, 11.6, I would say, and 11.8. So we got about a minute left here. Hopefully those balloons are losing a little bit of charge to the air. Like I said, it's leaking, the charge will be leaking off into the air. So then what will happen is with the repulsion getting less, they'll sort of swing down because gravity will pull them down and the repulsion won't be able to counteract gravity as much. So we got about another 30 seconds here, and I'll snap another picture and get my angle readings after that. It's actually not dropping much, so I guess my dehumidifier did an excellent job in here getting all the moisture out of the air because we're not losing much charge here. About 10 seconds left. Get the camera ready. Okay, so there we go. 2 minutes later, yeah, we got on one side, we have approximately 11 point maybe 4 and 11.1 or so. So I'm going to jot those down, maybe 11.3 and 11.1. Okay, so that's it for the data collection. Let me just take this down so I don't have to be so close to the camera. You could see me a little bit. Actually, I do because I need to show you this. So basically what you're going to do on this analysis sheet, you're going to follow the instructions, of course, but what you're going to do here is on the right balloon, this one right here, you're going to draw a force diagram. So think about what forces are acting on this balloon. I'll give you a hint. There are 3 of them. I already mentioned 2 of them, okay? There's a third one. Think about what physical object could be actually acting on that balloon, adding a third force, if you look at this picture. So force diagram, 3 arrows here. There's dotted lines here for reference to help you draw those arrows in the right proper direction, forces on that balloon. So what you're going to do in step number 7, okay? So step number 7 right here, you're going to develop an expression for the charge on the balloon in terms of theta, m, and r. In other words, you're going to solve the problem with only symbols, no numbers, because again, the numbers don't come till the next page anyway. So this is all with symbols, okay? And then step 8 is to use the formula from the previous step and solve for the charge in terms of theta, m, and l, not r. So you're eliminating the variable r in terms of l and d. Okay, so there's going to be some substitutions that happen here. So finally, you got a formula here for the charge of the balloon based on the data. No data yet, right? You flip the page, and then, like I said, you're going to be assigned your own data. These are my measurements, but you'll look in a spreadsheet and you'll pick your date up, and then you'll plug in the thetas and whatnot into the formula here to get a charge in the beginning with these angles over here. And then with these angles, you're going to re-plug in the new angles into the same formula, and you're going to get a charge in the beginning, a charge in the end, and then down here you're going to calculate the rate, how much I think let's see, that's number 16, coulombs per second. So remember, the time was 2 minutes, so you have to figure out how many seconds that is and figure out the coulombs per second loss on the balloons. And then from there, there's just a few questions, and that will be the balloon lab. Okay, so I hope you enjoyed the balloon lab here in my basement. I really enjoyed having you as a lab partner, and I'll see you in the next physics experiment.